Good evening all. Welcome to week 6 of the lectures. I'm Durga Prasad. So this session is aimed to help you solve your assignment problems as those who are joining for the session for the first time. We'll wait for a couple of minutes for a few more students to join and then we'll get started. To introduce myself, again, I'm Durga Prasad. So I'm a PhD scholar in IIT Madras. So the aim of these video lectures, or if you're seeing from on YouTube, is essentially to help you solve your assignment problems. If you have any doubts during the weekly sessions, you can ask them even in the discussion forum, or you can also post the questions, or you can discuss in the live sessions that we are having organizing every week on Saturdays. I'll quickly give a summary of all the topics that are discussed in this particular lecture videos discussed for this particular week, and then we'll solve problems. Once I cover the quick recap of all the topics, then we'll wait for some time so that if you have any doubts or queries, we can discuss them and then we'll go to the problems. So this week is mostly discussing on the equivalence between extreme points and basic feasible solutions. We discussed both these definitions last week, and then the concept of separating half plane, duality theorems, weak duality and strong duality are discussed in this week. These are the main topics for this particular week. So we have an LP problem in a standard form defined as follows. You try to minimize some function. X is my decision variable. C transpose X, this is called my objective function. These are my constraints. And this is my decision variable. Right? This is the standard form of LP. We discussed this even in last week. This is equivalent to the form where you have minimum C transpose X subject to two set of inequality constraints. Then we introduce the slack variables and then we convert them into equality, provided they are all positive. Slack variables are all positive. This is something we discussed even in the last book, so I'm not going to discuss that again. Here there are a couple of other conditions that A needs to be a full row rank matrix and B needs to be positive. That is just to ensure that for the way we formulate is unique for any problem. Now, let's say we define a set P such that Ax equal to B and x not equal to 0. Then it has at least one extreme point. And then suppose we say that P is a set such that it has at least one extreme point. Then what we can say about it? We can split the matrix A into something like this. So if you see here, A is a matrix of m by n. N is the variable dimension. And m are the number of constraints. Hi, good evening. Yeah. So we can split the matrix A. So I'm just covering a recap of all the topics, and once we cover, we can have if you have any doubts, we can discuss, and then we can also solve some problems. Yeah, you can post in the chat box as well. Sure. Okay. Yeah. So the matrix A can be decomposed into something like this. A is an m by n matrix, so we can divide it into the m rows, and we can also say it as the remaining columns, n minus m columns, so that this will be matched. So when we split it something of this sort, then we say A is a full row rank, so this B matrix can be invertible. B matrix is invertible, so we can write X as B inverse B and 0. Like if we can take all the remaining values to be 0, then we can calculate this the remaining values. So for example, X can also be written as n 0, something like this. Then if I multiply this A with this X, then we have B times XB equal to the small p over here. So the only this again, this B, maybe I should put B prime or something. So these are essentially the B's, the first m B's. These are the remaining n minus m. Sorry. B inverse B should do. So this is A times x equal to b. So we have b times xb, the set of basic solutions equal to b. So xb will be b inverse b. So this will be of dimension m, and this will be of dimension n minus m. So there should be m components that are given by this equation, and the remaining n minus 1 are 0. So these are the set of basic feasible solutions only if these values that we have found are greater than or equal to 0, because that is a constraint that has to be satisfied. Then we call those set as the basic feasible solutions. So what we are trying to say now is whenever we have an extreme point, then we are going to have a basic feasible solutions. So these extreme points are the basic feasible solutions. That is the main equivalence between here. So what we have is we define the set P, that is our feasible region, x such that Ax equal to Bx greater than or equal to 0. This is my feasible region, and a matrix A mapping from R m cross n, and it is full or rank. Then we say that if this particular x is an extreme point of P, then that particular x is also a basic feasible solution, and vice versa. So this is an if and only if condition. The derivation of it you can refer to the lecture videos, but the idea goes in like you can understand it in a very simple way. So if it is a basic feasible solution, we just now define that it is something of the form x equals to b inverse b. So this b is unique because out of the m rows you have only m linearly independent columns. So this b inverse b is unique, which means you cannot get two different x values. If you recall the definition of an extreme point, it's basically a point that cannot be decomposed into two other distinct points. So, and both the distinct points should eventually be again b inverse b, because b inverse b is a fixed value. You will always have the particular point x to be an extreme point if it is a basic feasible solution, and vice versa. The other one is a little complicated. You can go through the lecture video for that. Again, the idea goes in a similar way. You take a feasible region, you start with some point, you assume that if this particular point x satisfies the set of equations, you take whether x plus epsilon and x minus epsilon. If both x plus epsilon and x minus epsilon satisfy the same conditions, that is a times x plus epsilon equals to b, and a times x minus epsilon equal to b, then we already have x also satisfying the equation. So all three taken together will give us a times epsilon equal to 0. But we know a has only something like this. Should be 0. So now I have two different. So now I have a case here. So I can take b epsilon b equal to 0. If I take something like this, b is invertible, which means determinant of this not equal to 0, which means epsilon b should be equal to 0. Ideally, we'll have plus. So I can take this entire expression to be equal to 0, and this expression, if this particular expression is 0, then we have n times epsilon n equal to 0. And here n is the determinant of n is 0, because these are linearly dependent rows. We do not whether it can be dependent, independent, anything. So we cannot say anything. So it can be that this determinant will be 0, and in that case epsilon can be any value. If epsilon can be any value, it means there are multiple points, which means when you have two different points, then you can always take a linear combination of them in between. So that particular x will not be an extreme point. For an extreme point, if it is an extreme point, something like here, only x minus epsilon will be possible. X plus epsilon will fall outside the domain. So you cannot have x plus epsilon, x minus epsilon at the same time. So in a similar argument, you can extend this and say eventually that the only possibility is for this epsilon b to be 0, and the epsilon can be any quantity, which cannot be true. So which means the corresponding x for this epsilon n should be 0. Only if xn equal to 0, then we will have xb equal to x that we have defined previously, or let's say xp. So when all the xn are 0, and then we have a set of values of xp with epsilon b equal to 0, then we'll again have a matrix, something of this sort, xp and zeros. And this is the form we have for basic feasible solution. These are just some points from the same definition. If this particular P is the set of all my feasible solutions, is non-empty. If it is a non-empty, then definitely P is an extreme point. If there exists an optimal solution, then an extreme point then one of these extreme points will be the optimal solution. And the maximum number of extreme points that you can take for a given combination is you have an n by m matrix. Sorry, m by a is an m by n matrix. Then I have to convert it into something like this. So I have to pick m elements out of n elements. The number of ways I can do it is the NCM. So that gives me the maximum possible number of extreme points. This is all something we have discussed even in the last couple of weeks before. And next comes the concept of duality. So this is our primal problem. we have minimized C transpose X subject to the condition Ax equal to B and X greater than equal to 0. In the dual problem, the formulation becomes as the minimization becomes into a maximization problem. Instead of previously what the constraint will go into my objective, and again the objective will go into the constraint. The equality will be changed into inequality. So these are few changes. So minimization converts into maximization. The constraint will become an objective, and the objective will become my constraint, and equality becomes inequality. With these changes, the first one is called a primal problem, and the second one is called the dual problem. If you see the feasible region for both of them, for example, the feasible region here is basically the subspace of X, and the feasible region in the dual problem is a number of ways, the allowed values for the variable y. The dimension of X here is Rn, while the dimension of y here is Rm. So both are from different domains itself completely. So X and y, or to put it mathematically, you can write it as X such that Ax equal to B, X greater than equal to 0, and y such that this particular condition is satisfied. So these are your feasible regions. Even the dimensions are different for both X and y, but the A, B, C, and matrices that we have defined here are the same. So how are these two related? But as we see it, this superficially, they seem like this is a completely different problem, and this is a completely different another problem. But then there are two other statements where the weak duality statement says if either primal or dual exists, if one of them, if the optimal value exists for one of these, the another must also exist. Or to put it in different way, if one of them is unbounded, so if for example the minimum value for a primal is minus infinity, then the dual problem, the solution for a dual problem will not exist. In a similar way, if the maximum value is plus infinity for the dual problem, it will not exist. So you can write it simply as the optimal value of primal will be greater than or equal to the optimal value of dual. So if this particular thing, if the optimal value of primal is unbounded, which means this is minus infinity, then the dual problem should be some value which is less than minus infinity, which is not feasible. Similarly, if the optimal value of dual is plus infinity, then I would require the optimal value of primal to be greater than the plus infinity, which is again not feasible. So this entire statement can be written in this one expression. The optimal value of primal should always be greater than or equal to the optimal value of dual. But then this is called a weak duality because we have an inequality over here. In the strong duality, what we say that if any of these exist, then other will also exist, and both of them will be equal. So all the strong duality says is if they exist, both will be equal. And to prove that, the concept of separating hyperplane comes. The derivation is a bit lengthy, so I would, if you want to go through the derivation, you can actually refer to the lecture videos. But the main idea there is, I can explain what the basic idea is. So first, the concept of hyperplane, separating hyperplane will be introduced, where you have a convex set. And what we try to do is we take a convex set, we take another point, we take some point x, and we try to see, so maybe we try to separate both of them with a hyperplane denoted by the equation say A transpose x equal to B. And we say that this hyperplane separates this entire set from this particular point only if we have, okay, maybe I should put a different thing here, A transpose x star, and this is x belongs to C. Then A transpose x star should be, since if you take the origin somewhere over here, if you calculate the distances, the distance of x star should be less than this hyperplane distance, which is B, is less than any other point that you can possibly consider here, where x belongs to C. If such a thing exists, what the hyperplane theorem says that when you have a convex set and x star is a point that is outside the convex set, then you can always find a hyperplane that can separate this point from the convex set. If this is not convex, then you cannot find this hyperplane. That's the basic idea of the separating plane theorem. So what we try to do is to understand the relation between primal and dual. So if you recollect previously, so the primal search space is Rn, dual search space is Rm. So I cannot directly compare both of them. So first I need to convert them into a common space. So that is where the other spaces are introduced, where in the lecture videos we will introduce a space which is of dimension n plus m plus 2. And from this we'll take a projection to another dimension which is of m plus 1. And in this projection, we will construct a convex set, something like this for the primal and something similar like this in a dual. And then we will see that both of these indeed, like both of these will actually touch at only one point. We try to find a point that belongs to this particular set, and whether we try to construct a hyperplane that is separate both of this point with the entire primal space, and then we will eventually find out that they cannot be separated by long distance because of the weak duality, and eventually you'll find that both of them will actually be something like this, and both of them meet at only one common point, and that common point will be the optimal solution in that space. The optimal value, say Z star or something. The Z star will be of different dimension. The X star, Y star values will not be same. X and Y will be different values. But the optimal value, that is the Z value that you get, will be the same. That's what this theorem says. The X and Y values might be different, but the optimal value will be the same. So this is some kind of the contour for your optimal value or something. Then both of will meet at the same Z value. That is, I mean, the steps through which the derivation goes are a little involved. It will take some more time, so I'm not discussing them currently. Yeah, so these are the main topics. Broadly, the first I introduce what is strong duality, weak duality, and then we discuss the relation between primal and dual problems. And then the initial concept says that whenever you have an extreme point, then it will be equal to the number of your basic physical solutions. These are the main two concepts that I discussed in this week. Yeah, I don't think there are any questions in these topics. Yeah, so we'll quickly go through some problems. So we have a matrix A that belongs to Rm by n with the full row rank. The number this we have discussed just now. The number of extreme points is upper bounded by the maximum number of extreme points that you can take is basically the number of linear independent rows that you can construct. Sorry, number of linear independent columns that you can construct with from the matrix A. So that will be NCM. Let us have a set A defined given by this such that x transpose x is less than or equal to 4. Then which of the following is true? This is a convex set. Let me start with that. So is A convex? And maybe I should ask is, how do we know it is convex or not? We just take one point x1, we take another x1 belongs to A, we take another point x2 belongs to A, and then we take combination alpha x1 plus 1 minus alpha x2 such that alpha belongs to 0, 1, and then we check whether x belongs to A or not. This is what we do. So x1 belongs to A, which means so if I take x equal to alpha x1 plus x2 and check whether it satisfies that, we'll have as you can see, this is definitely not linear, so it cannot be polyhedral anyway. Anyways, you can directly see even without solving all of this that this may or may not be equal to 4. But can we say anything about whether this will be less than 4 or something? We know that this particular quantity over here is less than equal to this is always less than equal to 4, and this particular quantity is also less than equal to 4. So the maximum sum of this alpha is a positive quantity, 1 minus alpha is a positive quantity, so this is also a positive quantity. So the maximum the value that it can take is 8 alpha square plus alpha into 1 minus alpha into 8. This is the maximum value that this particular thing can take, and it is always positive. So the maximum value is, it should be less than 4. If this is less than 4, then x belongs to convex set. So you can just verify that. It will be alpha square plus alpha minus alpha square. This is 8 alpha. Since alpha is 0 to 1, so this will be somewhere between 0 to 8. But I want by this value to be less than or equal to 4, and this should be true for all alpha, which may not truly hold here. I think that it's a mistake somewhere, calculation mistake. This is actually a sphere. If you see x transpose x, this is basically, if you consider in R2, this will essentially be x1 square plus x2 square less than or equal to 4. This will be a circle. In R3, if you consider, this will be x1 square plus x2 square plus x3 square less than or equal to 4. So this is a circle and this is a sphere. A sphere or circle, whichever one you consider, they are not polyhedrons, but they are actually convex sets. You can consider any two points, and linear combination of any two points will always fall inside that. I think I messed up with calculation somewhere. I'll upload the correct one when I upload them on the drive folder. But it is intuitive, and it is actually, you can understand it from geometrically. Since this is a sphere, it will always be a convex one. And a convex set for a sphere, if you consider, you always have an extreme points. And what are the extreme points? Extreme points are when the radius will be equal to this particular value over here. So that is this. Whenever x transpose x equal to 4, you are at the boundary point. And those are the set of extreme points. Those points can never be split into any other 2 points. The same up here. You can think of this easily when you have a circle. In a circle, the extreme point occurs when you have x1 square plus x2 square equal to 4. Those are the boundary points. All the boundary points will be my extreme points. It's true for both circle and sphere. Yeah. So we have a set P such that x belongs to R2, and 1 is again a vector of 1s. X is less than or equal to 2, x greater than or equal to 0. How many x points does P have? So x is the second dimension. I mean, it's in R2. So how many extreme points does it have? So we already have the formula. It is NCM. All we need to find from this problem is what is n and what is m. N is the dimension of the problem. In this case, it is mentioned that x belongs to R2. And m comes from when you write it in the, okay, let me stop for a second here. So is this 2? Like, can I write this dimension of variable as 2? So to do that, the first step I have to check is whether this particular form that is written here is in the standard form or not. So if you write this, so the equations that I have are of the form ax less than or equal to b. This is not a standard form. So first I need to convert it into a standard form. So how do I do that? I just add one more slack variable. So 1 transpose x less than or equal to 2. So this is basically something like this. I said x belongs to R2. So it will be x1, x2 less than or equal to 2. So what do I do? So I add one more slack variable. So the equations here are x1 plus x2 less than or equal to 2. So I add a slack variable s1 equal to 2 such that s1 is greater than or equal to 0. Now I have 3 variables. So the set of equations now becomes 1, 1, 1. I have x1, x2, s1 equals to b, that is 2. And then I have x1, x2, and s1, all of them greater than or equal to 0. So this is in the standard form. In the standard form, the dimension of this is my A matrix, This is my X matrix and this is my B matrix. So A is of dimension m by n. So you can see the dimension here. So from, if you compare this and this, so this is a 1 by 3 matrix. So n is, so from here, if you compare this and this, we directly get m as 1 and n as 3. So the number of extreme points that we have is NCM, that is 3C1. Okay, is this clear? Okay. I think there are no questions in that. Okay. Now let's consider again a similar problem. This is on with respect to the weak duality and strong duality theorem that is stated. So we have a set P such that Ax less than or equal to P is true, and consider an, yeah, optimal solution. This one, right? We have. Okay. Yes. Okay. Yeah. So we have a set P such that Ax is less than or equal to B. So this is a polyhedron. And we have the problem, LP problem, such that maximize T transpose X such that X belongs to P. So this is not in the standard form. If P has an extreme point and the LP has an optimal solution, so there are two things that is given. One, it says that you have an extreme point, and the other, it says that it has an optimal solution, which means you have a bounded optimal solution. Then we can use the theorem that we said before, that whenever we have the LP problem, at least one solution will, the optimal solution, at least one of these extreme points will be an optimal solution. This we discussed a couple of weeks back. So we can use the theorem and say that the LP has an optimal solution, which is an extreme point in P. This is exactly a statement of from the theorem. So this is true. So whenever you have an extreme point, the extreme point, one of these extreme points of the LP problem or the polyhedron will actually be the solution, optimal solution for the LP problem. Okay, this is somewhat a theoretical question. So you have two LPs, two linear programming problems. The first one is T transpose X such that Ax equal to B, and the second one, this is a maximization problem, and the second one is minimize D transpose X Ax equal to B, where D and C are not equal. The basic feasible solutions of both the problems are the same. So the basic feasible solution is basically as discussed before. So if X is your variable, so basic feasible solution is something of this sort. First we take the vector, the matrix A, and then we decompose it into something like this, where this is the set of all linearly independent columns of A, and these are the whatever the remaining columns are there. And then if this B is invertible, then we write X as this. Since this is a linear independent rows, you can always, the determinant will be not equal to 0. So you can always take an inverse with respect to B and zeros. This is a general form of a basic feasible solution. So now if we see that here, both the matrices have the same values of A and B, which means this B is going to be same and B inverse is going to be same and B is also going to be same. So the X that you are going to get here will be same for both of them. Even though the problems are actually different, we don't, the objective function here is C transpose X and C and D are not equal. The objective function is different. So the optimal value that you are going to get might be different, but the set of basic feasible solutions is just same. So it's essentially because you have the same domain. So if you remember, if you recall, it is the same domain. Both of them are in the same feasible region. So you are going to have the same extreme points. But which of those extreme points is going to be the optimal value is what decided by the objective function, the C and D values. So for this problem, the feasible region as well as the basic feasible solutions are the same. The extreme points will also be the same. Clear? Yeah, I think this is clear. So we have a primal dual pair of LP problems. Both the problems have the same set of basic feasible points. Can I say something for the primal dual pair? This is a different. Okay, this is not a primal dual pair. So if you recollect in the stand, if we say this as a primal problem, which is not, because the standard form is this should be minimization. So let me say this is the primal form. Let's say this is the primal form. Then the dual form, in the dual form, this equal to gets converted into an inequality sign, which is not true. These two are not primal dual forms. But if you, let's say you have a primal dual pair of LP problems, and both the will both the problems have the same set of basic feasible points. So the primal problem is something like minimize C transpose X such that A x equal to B and you have X greater than equal to 0. This is my primal, and the corresponding dual will be, first the minimization converts to a maximization problem. The objective will be replaced with the constraints, and a new decision variable will come, B transpose Y, and you have A transpose Y. Equality gets converted into inequality, and the objective becomes the constraint. So this is my dual problem. So if you see, the domains itself are completely different. So here we are searching over X space, which is Rn, and here we are searching over Y space, which is Rm. The domains itself are completely different. So the set of basic feasible solutions, even the dimension won't even match. So they don't, they basically won't be of same feasible points, even if the domain matches somehow. So let's say you have a scenario where your number of constraints is equal to your number of variables, so that this n m n are equal. Even in that case, there is no guarantee that the same set of basic feasible points are going to come, because the polyhedrons itself are changed. If this B and C are not equal, if B and C are not equal, then the polyhedrons that they represent are completely different, and then which means their extreme points will also be completely different. If their extreme points are different, then the basic set of basic feasible points will also be different. So a set of primal dual pair will not have the same set of basic feasible points. I think this is clear. This is also just to see how the conversion is done. So here we have the primal problem defined with a maximization here. This means put one by one. So this is maximization. This is my objective. This is my constraint, and this is my inequality. And I want to convert it into a dual problem. We make the changes one by one. So the first one, the maximization should convert into a minimization problem, and then you introduce search variable y. And the second one, the objective and constraint should be reversed. So this should be my second one. And then comes the interchange of objective and constraint. So this b will be replaced with c. That is my third point. And last one is the inequality should be replaced with my equality. So if this is the primal problem, the corresponding dual problem will be something like this. The maximization converted to minimization, one by one, you see. The max converted to minimization. This converted into the constraint placed in the objective. The constraint in the original primal will be converted into the objective, and then the inequality will get converted into equality. So these are the main four things that you have to do to transform from primal to dual. Okay, and then since there is no constraint here, we also have y positive. This is the extra thing that we all have previously. So this is just the reverse. If you see that if this is the primal problem, this is the corresponding dual problem. So you can always do the reverse. So if this is the primal, this will be the dual, and if this is the primal, this will be the dual, or the vice versa. Yeah. Now I have a couple of couple of problems which tells you how to formulate a LP problem. So we have a company that produces both interior and exterior paints from two raw materials. So the raw materials are M1 and M2. So this 6 is basically, in order to produce exterior paint, you need 6 units of M1 and 1 unit of M2. Similarly, in order to produce 1 unit of interior paint, you will require 4 units of M1 and 2 units of M2. So it's like if you want to make some dish or something, you might require 6 spoons of say this is sugar and 1 spoon of salt or something, or chili powder or something. And similarly for the interior paint you have some other combination. And we also have the maximum availability of M1 and M2. So this is basically the stock that is available in your house or something. So this is the total stock available for material 1 and this is the total stock available for material 2. Now when I produce this exterior paint 1, I can sell them at 5 whatever unit, 5 rupees or 5 million rupees, 500 rupees, whatever, the corresponding scale is already taken care per unit of the exterior paint that you can sell. And similarly 4 for the unit of interior paint that you can sell. So these are the profits per unit. And there are a set of other constraints that says that the demand for the interior paint cannot exceed that for the exterior paint by more than 1 unit. And also the maximum daily demand for the interior paint is 2 units. And that particular company wants to determine the optimal product mix of the interior and exterior paint that maximizes their total daily profit. This question, we are not trying to solve the problem, we are just trying to formulate the problem. All we need to do is, we know the standard form of an MP problem, so we try to minimize something like this, such that Ax equal to B and x greater than equal to 0. All we need to do now is find what this C, A, B, X are. We just need to write equations that so that we can convert it into this form. How to solve that problem is not, we are not trying to do that now. Okay, so what are the decision variables here? What am I trying to find? We are trying to determine the optimal product mix of interior and exterior paints. So let's say the interior paint is say X1 and exterior paint, let's say it is X2. So what we are trying to do is, what should be the value of X1 and X2 so that your profit is maximized. So the profit, we already know how much we are going to make by selling 1 unit of exterior paint and 1 unit of interior paint. So you have 5 times, if this is X1, X2 and this is X1, the profit is going to be 5 times X2 plus 4 times X1. So this is the profit I have. So this will be my objective function. The constraints are basically one in terms of material constraints. So there is a limitation on the total material M1 that is available. So if I want to produce 1 unit of X2, so I would require, say for 1 unit of exterior paint, I would require 6 times the, so this is basically for 1 unit, I would require 6 units of MX1. So 6 times M1. And again here, sorry. So this 24 is basically the total quantity that would be required. So for 1 unit of X2, I would require 6 units of M1. So for X2 units, I would require 6 times X2 of M1, and then 4 times X1. Again for interior paint, for 1 unit of interior paint, I would require 4 units of M1. So for X1 units, I would require 4 times X1 units of M1. So this is the total quantity of M1 I can do, and this is the maximum availability. So it should be less than or equal to 24. This entire thing that I can use, this is the total quantity I can use for M1. And this is the available M1. So the total used quantity should be less than or equal to the available quantity. The similar logic applies for M2 as well. So you'll have X2 plus 2X1 should be less than or equal to 6. The same logic goes here. So used quantity of M2 should be less than the available quantity of M2. So these are the two constraints now from this particular table we can formulate. And then we also have additional constraints that says that the demand for the interior paint cannot exceed that of the exterior paint by more than 1 unit. So if I write all those things here, so the equations that we got here, 4x1 plus 5x2 subject to the constraint, 4x1 plus 6x2 less than or equal to 24, and 2x1 plus x2 less than or equal to 6. Now we have this extra constraint that says the demand for the interior paint cannot exceed that for the exterior paint. So the demand for the interior paint is x1, and it cannot exceed, sorry, it cannot exceed, which means it will always be less than or equal to the demand of the exterior paint plus 1 unit. Also, the maximum daily demand for the interior one is less than or equal to 2. So these are the set of all constraints for this problem that we can make. And we always have that I need to produce something always to get any profit. I need to produce something. So x1 and x2 both should be positive. So these are the set of constraints that I have. Now I have to convert this into the standard form. So how do I do that? First we introduce the slack variables. So we write maximize x1, x2, or let's just put x here. I'll just leave it so you know that whatever variables are there, with all respect to all the variables you are maximizing, the objective 4x1 plus 5x2, and then subjective to each of these constraints. So you have 4x1 plus 6x2 plus s1 equal to 24, 2x1 plus x2 plus s2 equal to 6, x1 minus x2 plus s3 equals to 1, and x1 should be less than or equal to 2, so x1 plus s2 equal to 2, and we also have the extra one, so x1, x2, s1, s2, all of them should be positive quantities. So this is my standard form. So if you now you can write it in the matrix form. So my C transpose will essentially be 4 and 5, 0, 0, 0, all the remaining ones will be 0. My X will be all the variables that I have, and A will be the big matrix that I have here. From the first equation, it will be 4x1, 6x2, 1. The remaining 3 will be 6. Sorry, there are a total of 6 variables. Yeah. So the next one, 2, 1, 0, 0, 1, 0, and the last one. So this is my A matrix. And similarly, I can write my B matrix. Now I know what is my C, what is my A, what is my B, and I have the constant x greater than or equal to 0. Now this defines my LP problem completely. So we have converted from words to this problem. Now you can see here that I have this is a 4 by 6 matrix. So I can always take 4 linearly independent rows. Sorry, 4 linearly independent columns, something like this, or you can also split somewhere here. This is much easier to understand. Okay, maybe I'll just remove the previous one. So I can split it something like this. So if I split it something like this, I have an identity matrix here, and all the columns are linearly independent. So with this split, I can formulate my set of basic feasible solutions. I can consider this matrix to be my B. I can consider this matrix to be my N. And what I have to do to get the basic feasible solution is just do the inverse of it. So my set of basic feasible solutions will be B inverse B and 0. B inverse is basically identity matrix. I'll just put B here so that it's clear that, or let me just leave it like that. So you can see that when I take an inverse of this will be identity matrix, and if I multiply that identity matrix with this quantity here, it will give me the same value B, and which all the values here are positive. So which means this is a basic feasible solution. So one basic feasible solution is this particular values. So again, if you see which rows, which columns you are taking here, these 4 columns are corresponding to the last 4 vectors S1, S2, S3, and S4. So when I'm writing X, I should be little careful here. So X1 and X2 I have not considered while doing the B. While constructing the B matrix, I did not consider X1 and X2. So the corresponding those values should be 0, and these 4 values are corresponding to these 4 columns. So when I do the inverse, so this will be 24, 6, 1, and 2. So this is a basic feasible solution. This is one of the basic feasible solution. It only takes care of only one extreme point. You can have different ways of constructing, just as I said. So you have 64 combinations. That is 15 combinations. So you can take 15 combinations, then you will get 15 different points like this, and out of those 15 points you substitute each of them into this particular objective function, then you will get a particular value, and then you compare these 15 values and see whichever one is the minimum, and that will be the optimal solution. That is a brute force way of doing. We have even clever ways of doing that. There's something called simplex, which which helps you to, instead of searching for 15 points, you can convert in say 2 to 3 iterations. Simplex is not discussed in this week, so we're not going to the method, but the idea should be clear now. This is how you calculate a basic visible solution. Are there any questions in this part up until here? Yeah, I think it is clear. There are a couple of more problems in the same way, so once you solve them, it maybe get even more clearer as you see. So this is another problem on for your reference. All these problems are taken from the book. I have given reference at the end. You can also check the book yourself. So you, for example, you want to invest say 5,000 rupees over the next year in two types of investment, A and B. They have different yield rates, and the research recommends that you need to invest at least 25% in A and 50% in B. And moreover, investment A should be at least half the investment in B. So again, you have to kind of decide what your objective is, what your decision variables are, what your constraints are. Here I didn't specify what the objective is, but let's say the objective is to maximize your E. So the question is, I need to split this amount into two amounts. So let's say XA is the amount invested in A, and XB is the amount that I'm planning to invest in B. The first question is clear. So how do I get, these are my decision variables. Now I need to come up with my objective function. Objective function is essentially my E. So I want to maximize my E. So that will be something like maximize. The yield is 5% in A. So something like this. And 8% in B. So this is something that I want to maximize. I can always take this 5xa plus 8b, the scale version, like we have referred previously also. Whenever you do a transformation by scaling, if you scale all of them with some positive values, then your optimal solution, the x star, will not change. If you just change this value to something else, so if I just put 5 and 8 or multiply this entire thing with 100 or 200, whatever it is, the value of objective value might change, but the solution, that xa and xp, that is what I want to know. These particular decision variables are not going to change. This we discussed in, like, I don't remember exactly, maybe week 4 or week 3, when we discussed on transformation of optimization problems. So this is my maximization. So what are the constraints? One constraint is the total amount that I have, that is xa plus xp should be equal to 5,000. Again, here it's again subjective. So you can say that if you want to invest entire money, then this will be equal to. If you say that this is the maximum amount of money that you want to invest, then you can always have the constraint saying xa plus xp less than or equal to 5,000. But for now, let's say you want to invest the entire money. So I'll just put an equal to here. And the other constraints are, the research recommends that allocation of at least 25% in A. So XA should be at least 25. So it should be greater than or equal to 25% of whatever money you are investing. So that is just XA plus XP. Or you can put it in your way, just substitute 5,000 here and then take it way, or let me just put it in this way. You just go with something like this. So this is the maximum amount that you want to invest, but you can always invest less. It's up to you. And then you have XP. It says that and at most 50% in XP. So XP should always be less than or equal to 50% of whatever total amount you're investing. Moreover, investment A should be at least half the investment in B. Should be at least half the investment in B. So these are the set of constraints I have, and I definitely want to invest something. So it's not like I won't invest anything. So this is the third last constraint that I have. Again, you can try to convert this into a standard form. So it would be again the straightforward thing that we have done before. First you introduce the slack variables, and then you convert it into the matrix. So let me do it straightly here. So since we have already done it before, I don't think it requires much more understanding, but there are a little of, here you have a greater than sign, here you have a greater than sign, you have to convert them into less than, equal to, and then add the slack variables. So this will be converted into something like 0.05 XA, 0.08 XP with the constraints XA plus XP plus say S1 equal to 5000. The next constraint is this will be 4XA. So if I take it on the other side, XP minus 3XA plus S2 equals to 0. And then I have XP minus XA equal to 0. And then I have XP minus 2XA equal to 0. And I have the standard conditions. Sorry. So we have this 4 here. And the last conditions that XA, XP and all the S values that I have considered should be greater than or equal to 0. So this is in the standard form. So now if you write it in the matrix form, my C matrix will be 0.05, 0.08, and the remaining all 4 coefficients will be 0. Okay, this way, so this should and then X is also the same. So you have XA, SP. This is just like what we had before. And you can take this in again in the matrix form. So your A will be 1, 1, 1, and remaining all coefficients are 0. S2, S3, S4. Similarly, minus 3, 1. Then you have the third one, XB, S3, and the last one. So this is my A matrix. This is my B matrix. Again, you can see here, I can always take these last four. So if you keep seeing the pattern here, so whenever you have these slack variables, you can always consider those slack variables first. So you'll always have like how many number of slack variables you have. So if you don't have any equality constraints, if all the constraints that you have are just the inequality constraints, then you'll always end up with something of this particular form. You'll always end up with an identity matrix. You can always construct some linear independent rows of m inequalities will form an m identity matrix. And once you do the inverse, it will be the same. So this particular value will be your first basic feasible solution, as long as you have all inequality constraints. Now let's say if you have one of them as equality constraints. So let's say instead of an inequality here, you have an equality constraint. You want to invest entire money. So which essentially means you are making S1 equal to 0. So this entire row disappears. Then then your problem changes a little. So then this and two things will go off. So if this thing is replaced with an equality, then what is going to happen is this S1 will be 0, this S1 will go off, so which means this quantity here will become 0. Then you can see that the remaining equations will remain the same. Only S1 will go, so this will also go. So this S1 will go, this S1 will go, and this particular value corresponding to S1 will also go. So then all of these quantities will actually go. So this entire row gets gone. All these things will just vanish. So now you'll be having with 1, 2, 3, 4, 5 columns. Out of these 5 columns, now you have to find one set of columns that are linearly independent, and then use that to determine the value of choose those matrix. For example, you can consider these 4 and check if you consider these 4, this one and these ones. If you consider these 4, they are not linearly independent. You can they are actually linearly independent. Yeah, they are linearly independent. So you can consider these 4, or you can consider this 2 and this 2. Any of the 4 you can consider, and then you can make the B matrix and then take the inverse, and then you will get the basic feasible solution. And if I consider the inequality constraint, then I basically have 6 variables, and I have 4, So this will give me 15 combinations of extreme points. But if I consider an equality, then one of the variables is reduced. So that will reduce my search combinations from 15 to 5. So if I decided that I will invest entirely, then I don't have to consider so many other extreme points. So there are only 5 possible scenarios that I need to check. But if I don't even know whether I'll invest entire money, maybe I'll save some of them out of both A and B. I want to keep in something else C. Then I will have to have even more constraints and even more extreme points that I have to search for. Okay. This is clear up until here. I think this is clear. There is one last problem again. This is also on the similar lines. So if the previous two problems are clear, I think I can directly write the equations here. Directly write the matrix equation. So you'll be able to, I won't need much explanation here. So here we have two different feedstuffs, corn and soybean. These are the different protein contents in them, and this is the cost associated with it. The objective is to determine the minimum cost fitness. So my objective, the decision variables are, so what will be my decision variables? So for example, I don't know how much corn to put and how much soybean to put. So let's say this is my x1 and this is my x2. So these are my decision variables. I need to determine how much corn and how much soybean that I need to put in my feed. So the first thing I have is at least I need to have a daily feed of 400 kilograms. So x1 plus x, okay, let's say the objective first. So this is 30 per kg. So the total cost, the objective will be 30 times x1 plus 90 times x2. So this will be my objective function. So I need to minimize this one, subject to the following whatever other constraints that I have. The first constraint says that it uses at least 400 kilograms of special feed. So whatever I have x1 plus x2 should be at least 400. So this should always be greater than or equal to 400. That is the first constraint. And then I have some dietary requirements that says that at least 30% is protein. So if I have say the protein content x1, then 0.09 of it will be protein. So 0.09 x1 plus 0.6 x2 should be at least 30%. 30% of what? 30% of whatever total weight I have of x1 plus x2. This is another constraint. Similarly, I have one more constraint in terms of fiber content. That is again goes in the same way. So you take 0.02 of x1 plus 0.06 of x2. At most 5. So this should be less than or equal to 5%, 0.05 times x1 plus x2. So again, this is my objective function. These are the three constraints. All of them are inequality constraints. So now how to convert them. So there will be three stack variables. The extra thing that I have is x1 and x2 should be greater than or equal to 0. So you can make the matrices to yourself. I don't think, or if you want, I can write them down. So you will have three slack variables. So one for each of these equations. The first thing you need to do is that this is a greater than or equal to sign. So you need to convert it into less than or equal to sign. So you write them down. So you want to minimize the cost. So minimize 30x1 plus 90x2 subject to the constraint x1 plus x2. If I want to convert it to less than or equal to sign, so I'll write it as minus x1 minus x2 should be less than or equal to minus 400. And then I have 0.3 minus 0.09, 1x1 and minus 0.3 x2 is less than or equal to 0. And then I have 0.03 x1 minus 0.01 x2 less than or equal to 0. And I have this inverse. Right. Now you can write it in the matrix form. You can add more slack variables here. So eventually you'll get your C. So if you write it in the normal way we are writing it, so it will be something like 30, 90, and you have three slack variables. C transpose, your X will be something like this, subjected to the constant Ax equal to B. A will be something like this, S1, S2, and S3. Now again, if you see, if you want to convert it into standard form, the first, when we mentioned initially, we want this B to be greater than equal to 0. That is the way we find it. So all we have to do is multiply this entire first row with the minus sign. So this becomes something like this. Then this will be my standard form. So this is my A matrix, this is my B matrix, this is my C matrix, and this is my C matrix. Again, now you can also do the same thing. So this is a 3 by 5 matrix. So you can always choose these 3 values. So this will form my linear independent columns. So I can always take B inverse B, and that will give me the set of basic, check whether all the values of B inverse B are positive. If they are positive, then those will be the set of my basic feasible solutions. But let's say, for example, if you have chosen these 3 and you did B inverse B, and then let's say they are not positive, then what you have to do is you have to take another 3 combinations. So instead of these 3, now maybe you can take these 3. With these 3 you will try, and one of them will be positive, and that particular one will be the basic feasible solution. Are there any questions in this up until now? So I think these are the questions I have for this week. Yeah. Are there any things that you want to discuss? These are just references from where I have taken the problems. Yeah, sure. Just to give a quick recap of what we discussed. So initially we started out saying that the equivalence between the extreme points and the basic feasible solution. We told that whenever there is an extreme point and the corresponding values of x that you have, that x being 0, that will be a basic feasible solution, and the vice versa. If you have a basic feasible solution, then it will also be an extreme point. That's the first thing that we discussed. And then we discussed the concept of duality. It's a primal problem. You have the how to convert from primal to dual is the minimum converted to maximum. The objective becomes a constant, constant becomes objective, equalities and equality gets interchanged into inequalities. That is the primal dual conversion. And then the two theorems come, that is the weak duality and the strong duality. The weak duality says that the optimal value of primal will always be greater than or equal to the optimal value of the dual. And in the strong duality, we say that this instead of inequality, we actually have an equality signal that both of them, if one of them exists, the other one will also exist, and both the values will be same. The values here refer to the optimal values. So the objective function value will be the same, but the actual values of x and y in the primal dual space might be different. Then in order to prove that, we need a concept of separating hyperplane where we took a convex set, we took a point x, and then we said that as long as x star is outside the convex set, we can always construct a plane such that these points are separated from each other. So that is called a separating hyperplane. And then there is some derivation that I kind of skipped here, which actually is given in the lecture videos, which actually proves that using the separating hyperplane, we can say that whenever you have a primal and dual converted into some common space, and so that the objective values will actually be same and they will be equal. That is something that I've skipped here. Then we discuss some of the problems. Most of them discuss how many extreme points you have and the different other ways of how to calculate extreme points in basic feasible solutions. Most of the problems are the same. And then we discuss on some relation between the primal and dual problem as well. So these are the things that I have for this week. Yeah. Thank you for joining. think if there are no other questions, I don't think there is anyone else. I think we can stop. We can call it a day, and we can meet next week. Bye. Thank you.